Bismillahirrahmanirrahim. Today we will discuss strain energy function and stability conditions. Our strain energy function. When a material undergoes a deformation, energy is expended to deform it. That you will have to use some energy to deform any material. Elasticity of an actual material results from the fact that a large part of energy. Now, what does the elasticity says? It says that when you deform a body and it means that you have expended energy to deform it. Then elasticity says that large part of this expended energy which you have used to deform the material is converted into potential energy stored within the deformed material. That when you apply the force on a material to deform that, then that we are talking about elastic material. When you apply the force on an elastic material to deform it, then that energy is stored in the material, and when you remove that force, then that energy which is stored in the deformed body as potential energy again works and bring back that material to in its original position. So elasticity says that a large part of used energy, expended energy to deform a body is converted to potential energy which is stored in the deformed material. That when you remove the force, then that stored energy will work to bring that material back into its original form. This is what elasticity says. No, for elastic continua is the plural of word continuum. For elastic continua, we suppose that all the expended energy is stored within the strained continuum. Here we are supposing that all the expended energy is stored within that strained continuum. We refer to this energy as strain energy. Strain energy is this word is coming from the word strained continuum. That we are supposing that all the energy which has been expended to reshape the continuum will be stored in the strained continuum. We refer that energy as strain energy, and a mathematical expression to represent that strain energy is called strain energy function. Now we will have to derive that mathematical expression which is strain energy function. That what is the form of strain energy function? We have assumed that all the expended energy is stored in the strained continuum, so we are dealing with conservative system. As we have supposed that all the expended energy is stored in the strained continuum, so it means that we are talking about conservative system, and we want to formulate potential energy function, strain energy function. So to deal with conservative force, we can write components of force in terms of potential energy as follows. That if you have conservative force, then you know that curl of that force will be equal to 0, and in that case you can write your F as components of your force as this. These are the components of that force. F is basically gradient of some potential energy V. F is equal to, if curl of F is equal to 0, then that F will be equal to gradient of some potential energy V. Gradient of some potential energy V. It means that F will be equal to del V, and then del gradient V, then that gradient V can be written as F is equal to partial V partial x1 E1 plus partial V partial x2 E2 plus partial V partial x3 E3. So each component can be written as Fy equals to partial V partial x. This is F1 is the first component, partial V partial x1. F2 is the second component, partial V partial x2, and F3 will be third component, partial V partial x3. So this is for the case of when we have conservative force. Now we will write by analogy of this equation as, here we have components of force, and we know that from Hooke's law F is equal to kx. F is equal to kx. F for the force in Hooke's law, and for the generalized Hooke's law we have strain, we have stress Tij equals toCijkl skl. Here F, component F, so we will write with the help of analogy the components of stress Tij. F will correspond to stress components. Here are force component F1, F1, F2, F3. Here are stress components, 9 components. And for left hand side, here we have written V. Here we will write W. Here is x, as we have said that for F is equal to kx, that function, that Hooke's law, x is, what is x? X is basically change x naught original position to x1 any position when we apply the force, then difference is x. Then we denote that x with our strain in generalized Hooke's law, Tij equal toCijkl skl. Similarly, here x will be changed by strain components. Here components are x1, x2, x3. Here will be Sij. So this is with the help of analogy using on this equation. Now we can write Tij equals toCijkl skl. We have to do nothing, simply we have to find basically W, which is strain energy function. We simply integrate both sides with respect to Sij. Then we have this thing, simply nothing. Now this is the strain energy function. This function is called strain energy function, and you can see that for unstrained state W is 0. W is totally dependent on strain. Whenever strain is 0, strain 0 means that we have no deformation, that we have unstrained state. So it means that W is 0. Strain energy function is 0 when strain is 0. Now let us see with the help of this strain energy function about the symmetry of elasticity tensor. In our previous lecture we have seen that our elasticity tensor is symmetric pairwise, in first pair and in second pair. What does this mean?Cijkl equals toCijkl andCijkl equal toCijlk. Symmetric in first and symmetric in second pair, first pair and second pair. Now we will see that our elasticity tensor is symmetric pairwise. Now this is the question. From here we have integrated this by SKL. Here will be CIJKL. So we have taken the derivative. Change I and j. Ij KL equals to C KL Ij. And we know that derivatives are, this is strain energy function is continuous and derivatives are also continuous. So we can write from 1 and 2. Cijkl equals to CKLij. So from here we can see that our elasticity tensor is symmetric pairwise. Now it means that for Cijkl we have written a 6 by 6 matrix, which was Cmn. So if we denote Ij by m and Kl by n, then it would be Cmn equals to Cnm. So it means that elasticity matrix is symmetric about the main diagonal. So you can see that when it is symmetric about the main diagonal, then it would have 21 independent components. So general elasticity matrix has 21 independent components. So we have seen that from our start, elasticity tensor has 81. Total number of components was 81. 54 when we have used symmetry of stress, then 36 when we have used symmetry of strain together with stress. Now we have seen that by using the strain energy function, we have seen that we have 21 independent components. Total number of components of elasticity tensor is 81, but 21 is independent. That if you know 21 components, independent components of elasticity tensor, then you can write the whole 81 components of elasticity tensor. Now stability conditions. As we have seen that strain energy function is formulated in terms of Cijkl. You can see that W is equal to 1 by 2 Cijkl Sij Skl. Now with the help of this function, this strain energy function, we have some restrictions on these parameters. So these restrictions, these constraints are called stability conditions. Now we will see that what are those stability conditions. We know that energy is positive, and conventionally strain energy of an undeformed continuum is 0. We have seen that when S is 0, strain energy function is 0. In general it is positive, and it is 0 when we have undeformed state, that when we have unstrained state, unstrained continuum. And we know that W is equal to this. We can write this thing in matrix form. S transpose S CS. Now here we can see that we have no free index, because this is energy and this is scalar, so there should be no free index. We have written this in this way. Here strain, this is 6 by 1 matrix, 6 by 1 row matrix. Sorry, 1 by 6 row matrix. and this is 6 by 6 elasticity matrix. 1 by 6, 6 by 6. This is 6 by 1 column matrix. This is 6 by 1 column matrix. This is 1 by 6 row matrix. So at the end, when you will multiply all these, you will have 1 by 1 single number. 1 by 6, 6 by 6, 6 by 1. After multiplication, you have single number W, which is a scalar. So we can write this in the matrix form in this way. And we know that W is positive. It is 0 when S is 0. So for deformed state, W is positive. So it means that this is positive. If this is positive, then we can write this is positive. And this is the result of positive definite by using the linear algebra, that any matrix say A is positive definite if X transpose AX greater than 0 for any X. Similarly here, so we can write that from this condition that our matrix C is positive definite. W is positive, then this is positive, then this implies that C is positive definite. Now we will see that what happens when we have positive definite condition. Now from linear algebra, a real symmetric matrix is positive definite if and only if the determinants of all its leading principal minors, including the determinant of the matrix itself, are positive. This is from the linear algebra. That linear algebra says that if you have real and symmetric matrix, then it is positive if and only if determinants of all its leading principal minors, including the determinants of the matrix itself, are positive. If it is positive definite, real and symmetric matrix positive definite, then these determinants of all leading principal minors will be positive. And if these are positive, then this is the positive definite matrix. And our matrix is real and symmetric. So determinants of all its leading principal minors, including the determinant of the matrix itself, are positive. Now these are here. It means that C11 positive. This is the second determinant. C11, C12, C21, C22. This is third leading principal minor. C11, C12, C1, 3 by 3, then 4 by 4, then 5 by 5, then 6 by 6. These are the 6 leading principal minors and determinants of leading principal minors. We have many minors, but these are only 6 principal leading principal minors for a 6 by 6 matrix. So you can write minor matrix for any entry, but these are the leading, and we are taking their determinants. So when these are positive, suppose this is positive, that as we have said that our C is positive definite. C is positive definite, and positive definiteness of C is coming with the help of strain energy function, because strain energy function is positive. If that is positive, then C is positive definite, and if C is positive definite, then we have all these results. And when we have all these results, then we can see that, for example, for this determinant we can write C11, C22 will be greater than C12 square. Then these are some constraints that product of C11 and C22 should be greater than square of C12. These are the constraints. Similarly, some from here, and some from 4 by 4, 5 by 5, and 6 by 6. And similarly, from first C11 greater than 0. No. This is the second condition, that again linear algebra says that a real symmetric matter is positive definite when all its eigenvalues are positive. No, our eigenvalues, if you want to calculate the eigenvalues of our symmetric matrix C, which is positive definite, then all the eigenvalues will be in the form of these elasticity constants. C11, C12, C13 something, their differences, their products, their sums, eigenvalues will be in the form of these constants. So we are saying that if it is positive definite, then eigenvalues will be positive. And when we write any eigenvalue positive, then it means that some condition must be come from that positive eigenvalue. Now we have one more condition, that all the diagonal elements are positive for C. We can prove this if you take or strain this and this is C. When you multiply all these, you have C11. You know that W is positive, so we C11 positive. You can prove all other C22, C33 with the help of following this procedure. So then, and you have all the diagonal elements positive. So these are some stability conditions, some constraints on the parameters of the elasticity matrix, and we call these constraints as stability conditions. This is the today's lecture. Thank you so much. Allah Hafiz.